Assalamu alaikum. This video tutorial is for a simulation study done on a PVT system using a custom absorber. First of all, we need to start up the workbench. I'm using the ANSYS 2019 R2 version. This is the workbench. From the workbench in the component system, import the geometry component and open it in Design Modeler. Now the Design Modeler is open. In here we will be designing the PVT system module virtually. To start with, just click on a plane. For me, I'm choosing the XY plane, and I'm gonna go to sketching and press this icon. Look at the face perpendicularly. Now we draw a rectangle and give it dimensions. So in my PVT system model, I have glass layer, PV layer, absorber plate, and the insulator, tube, water, and thermal paste. So how I'm choosing to approach this is first this is the glass. For glass dimensions, I gave as the thickness of glass is 0.003 meter, and the length should be, according to the experimental study from where I'm borrowing the dimensions, it should be 0.63 meter. So this is the glass component. Now go back to the modeling tab and you can see the sketch 1 is glass layer. Now to input another layer, we need to create a new sketch. In the new sketch, go to sketching, draw another rectangle on top of the glass layer. And once again, giving it dimensions. Length should be same, 0.63. And this is the PV layer and its thickness is 0.0003. Now we have the glass in PV layer. Repeating the same process for adding another layer. Once again a rectangle, giving it dimension. Length 0.63. Height of the absorber plate is 0.0004. Now on top of this one, we need to create once again another sketch, and this should be the insulation body. Giving it dimensions. Once again, length should be 0.63. Now the height of it, the insulation should what we call encompass the thermal paste and the tube and the water, everything. So adding up all the dimensions for water and tube that we are going to add later, I'm going to put 0.013 as the insulation layer height. Now we have all the what we call straight panel layers in place. Now we just click on a new sketch. We have sketch 6 here. Now it's time to draw the tube. For the tube, basically just draw a random line in the insulator body on a new sketch. Go to dimensions, click on general and on the line, and click on vertical on the line and the bottom line of the insulator body. So this is just to locate the center of the tube. Horizontal is the distance from the insulator left what you call boundary to the center of the tube. So in the design I'm borrowing, the tube is used as 0.012 meter. So its radius would be 0.006. If we put 0.006, but now the tube outer boundary will be in contact with the insulation boundary over here. So we need to provide some clearance so we can have avoid some problems in the mesh. Because if it's too tight in the meshing, we will have invalid dihedral angles, which will give us improper result. So instead of putting the radius, I just radius plus 0.001 so it should be 0.007. The vertical distance, the same thing, 0.006 would bring us to the center of the tube, but we need to give some clearance. In here I'm going to give the clearance of 0.0005. So the vertical distance to the center should be 0.0065. Now that we have the center, in the same sketch we can click on a circle in the middle point and draw a circle. Going to dimensions on general and give the diameter 0.012. As you can see, the tube is having some clearance to the boundaries, so there will be no problems in the mesh. Now we go back to draw and draw the inner boundary of the tube. The dimension for the inner boundary is 0.01. Now that we have the tube boundary, we can delete our guiding lines. There we go. So this is the tube, and just to be safe, we're going to fix the circle. So sketch 6 we see here is the tube. Click on the XY plane, generate another plane. In here we're going to draw a circle matching the inner boundary of the tube, and this sketch will be the water boundary. Now it's time to draw the thermal paste. Click on new sketch, go to sketching. The thermal paste body is there just to facilitate the contact between the tube and the absorber plate. So we're going to make it as small as possible. We click on a line draw a line across like this on the outer tube diameter, and we connect these lines to the absorber plate. Sorry, we complete the rectangle. After doing so, we will delete this upper line. Now click on arc by 3 point and click on these side points and align the arc with the outer wall of the tube. And just like that, we have our thermal paste. Before we go any further, we should draw the 3D bodies of the simple straight-sided plates, flat plates. To do that, just click on the sketch of any one of the bodies starting with the glass, sketch 1, and click on extrude. We apply sketch 1 as the geometry. Operation, we add frozen because these bodies are different layers, it's better to add frozen. Direction vector should be normal. The direction we choose as reverse. Extend should be fixed, and the width of the glass of PVT absorber insulator will always be the same, and it's 0.54. Merge topology, yes, and we generate. And now as you can see, we have the entire body. Now we repeat the process for all the other layers. Here we have all the flat bodies extruded. We will not extrude the tube, water and the thermal paste because we need to sweep them across a path of the absorber tubing, and we need to create the pathing sketch first. So to start with, we are going to create a new plane. The type we select from a point and the normal. The base point we select as the center point of the tube, and normal we select as the y-axis, and click on generate. Now along this plane we are going to draw the absorber line. This line will be the guide for the tube, water and the thermal paste bodies to sweep across. So here is the path we have drawn for the absorber, water, and the thermal paste, starting from this point and ending at this point. The dimensions are as follows. The first, what we call tubing, and the last tube, the space between them is 0.615. The space of the one absorber loop from start to end of a single absorber is 0.288. This is the connecting section of the two absorber loops, and the distance between them is 0.04. And in the middle, for geometrical purposes, to simplify the geometry, we had to change the pipe distance. And in these center sections, in both absorber loops, the pipe distance is 0.032. And the clearance between, we call the side of the absorber and the bottom edges of the PV panel, is 0.014 approximately. Once we have the absorber loop all drawn, now we can sweep our bodies of tube, water, and thermal paste. To do so, we're going to navigate to the sketch which holds the components. Here we are at the tube sketch, and we're going to click on sweep. Profile will be the tube sketch. Path we select as the sketching we draw. Apply. The operation should be slice material, as we are drawing the tube within another frozen body. No twist, no thin surface, merge topology, yes. And we click on generate. Now we have the tube. Not only the tube, but we automatically generated the water body, the tube body, and the insulator. Now to add the thermal paste, we select the thermal paste sketch, apply the same process. Add frozen, merge topology, and click generate. Now we have the thermal paste layer. In total, we have 7 bodies, all shown here. To simplify the meshing process, we are just going to put all of these bodies into a single part like this. And we're going to make sure we define the material type for each body. If it's a fluid, it should be fluid. If it's a fluid, it should be fluid. Changing water to solid from fluid. Now, the part is all ready. Now the only thing left is to apply name selection. To start with name selection, we're going to select the bodies. For example, this is the insulator body. We're going to apply the name selection, and we're going to name it as insulator. Click on generate. Like so, we're going to do for all of the. Here's the complete list of name selections I've applied: insulator, tube, water, paste, the absorber plate, PV plate, glass plate, the inlet face, and here we have the outlet face. And we also have the glass top and the PV top. These are the walls where we'll be applying some boundary conditions to facilitate the heat transfer. After we have everything, name selections included, all the parts, we can just export the drawing with any name and save. So this file, geometry file, we can open in a meshing software and start our mesh. After exporting the model body, now we're going to do the meshing. For meshing purpose, I'm going to use the ANSYS Fluent 2019 R2 version, and I'm going to open it in the meshing mode And this is the ANSYS Fluent meshing mode. From the workflow type, we're going to select the watertight geometry and going to the import geometry unit. Our unit is meter, so we're going to change it from millimeter to meter. And we're going to navigate to our exported geometry file. Here we have the geometry file. We're going to import. It's going to take some time, and there we go. Now our file is imported. Now this is the option of adding local sizing. What this will do is provide local mesh sizing for each of the different components. But since our geometry is simple enough, we're not going to do that. We're going to select no and going to update. In the create surface mesh menu, okay, so if it's minimum size 0.001, maximum size 0.0015, we're going to keep all the other settings the same, and we're going to click on create surface mesh. After taking some time, the surface mesh would be finished. And down here in the console box, you can check the maximum skewness of your mesh. Mine is 0.7.9. If the mesh maximum skewness exceeds 0.9, it will give you an error to say you need to improve the mesh. And if we need to improve the mesh, we can right click on create surface mesh, insert next task, and click on improve surface mesh. And this way we can improve the surface mesh. Because we don't need to, I'm not going to. We're going to move on to describe geometry. Since our geometry has both solid and fluid regions, we're going to pick the last option, which has both fluid and solid regions, but no voids. No capping, and no to this, not this, because all of our layers are already in a single part. We do not need to apply shear topology. In the update boundary section, we will have the name selections we have provided as the boundaries on the faces. So the glass top, the top face of the glass will be wall. Inlet is from velocity, we're going to change to mass flow rate, mass flow inlet. Outlet we're going to keep as pressure, and we have PVT top. Updating the boundaries, and this asking to estimate the number of fluid regions. We have 1. We're going to put 1 and create the regions. This will also take some time. After we have created the regions, Fluent is going to show me the regions so we can check and verify each of the region is correctly assigned. Glass is solid, insulator solid, solid, water is fluid. Every region is correctly assigned. We're going to move on to create volume mesh. Boundary layers we're going to keep as 3, keeping everything as 3. Method we're going to use polyhedra. Growth rate 1.2. Maximum cell rate length, you can put anything, but it will automatically adjust this number according to the surface mesh. And now we're going to create the volume mesh. Depending on your PC, it might take about from 15 minutes to an hour. So now that we have the create volume mesh, we can go to mesh, click on check quality, and we can check the quality here. Minimum orthogonal quality 0.2, and the aspect ratio maximum 27. Cell counts will also be displayed with the maximum skewness. After we have the mesh, we can now write the mesh file to a preferred location on your hard drive, and we're going to save. After I'm writing the mesh file, we're going to go back to the workbench and we're going to drag and drop a Fluent analysis system into the project schematic, and we're going to right click on the mesh and import the mesh file. You're going to browse to the mesh file we just exported from ANSYS, and we're going to open the mesh. After it's open, we're going to go to the ANSYS Fluent setup. We're going to start the Fluent in double precision mode and parallel mode with the amount of processors available in your PC. I'm going to click OK. Alright, now we have the mesh imported. In the Generals tab, we can check the mesh and report the quality, but we already know the quality, so we don't need to do that. In the Models menu, we need to turn on the Energy module and keep the Laminar module for the Viscous module. In the Materials tab, we need to add the materials. The material water, air, and wood, copper, aluminium. These are common materials that we can import from the material database in the Fluent, like so. From here, Fluent database, and from here you can add the common materials, fluid or solids. And for materials like glass, paste, PV, we have the properties from experimental paper. From there we can just create the materials like this, add the properties. Now I've done so already. Now it's time to go to cell zone condition. These are the regions that we created in the meshing, and we need to assign each region its appropriate material. For example, this region is glass and the material should be glass. After doing so for all of these cell zones, we will move on to boundary conditions. From here, I already know the meaning of these names, which name refers to what boundary condition. You need to make sure what boundary condition you're referring to. For example, this is the glass side wall, and we're going to keep all of the side walls as adiabatic walls. So we're going to change nothing, just keep the material as glass and click OK. The glass top boundary condition is where we will apply the solar loads, so to say. We're going to pick the convection option. Material should be glass. This is the heat transfer coefficient that we calculate for using a formula that is referred in the paper. The free stream temperature we're going to take from the experimental study, and we're going to convert to Kelvin and put here. This is the wall thickness of glass, 0.003. Heat generation rate is the incident solar radiation multiplied by the percentage of radiation that will be absorbed by the glass. So for the glass, I'm taking as 10% to be absorbed. And the incident solar radiation is 900, so I'm going to multiply 900 by 0.1, and we're going to get this one. In the mass flow inlet condition, we're going to put the mass flow rate, and we're going to make sure the direction specification method is set to normal to boundary. In thermal condition, we're going to put the inlet temperature. The what we call interface walls, like this one, insulator and paste. This is the interface between the insulator and the thermal paste. We're going to put the material as the adjacent cell zone material, and we're going to couple the thermal conditions. Keep doing the same for all of these interfaces. Now it's time for outlet. Outlet setting, we're not going to change anything. We're just going to make sure the backflow temperature is same as the inlet temperature. This is again the side wall, interfaces wall. Now this interface, no, sorry, this one, PV top is the interface between glass and PV. This interface we will be applying some boundary conditions, keeping it as coupled, material name PV, wall thickness we're going to use of the PV thickness. Now the heat generation rate here is the incident solar radiation multiplied by the absorbability of the PV cell. The absorbability I have taken as 0.9, so we're going to multiply 900 by 0.9 and we're going to get this value. This is the fluid solid interface, tube and water interface. Not sorry, this one. We're going to keep it as a stationary wall, no slip condition, thermal coupled using copper because tube is copper. And like that, we're going to set all the boundary conditions and we're going to move on to methods. In the method step, we're going to keep the pressure velocity coupling scheme as simple, gradients least squared cell based, pressure, momentum, energy as second order upwind. In the report definitions tab, we're going to add a report definition for field variable temperature, static temperature, and the report type would be area weighted averaging. This way we can get the average temperature in the outlet phase and on the PV tops phase. Okay. So after we do the solution converge, then we can come back here and compute the outlet and PV top temperatures. In initialization tab, we're going to use hybrid initialization, after which we're going to run the calculation. Now the calculation is complete. The solution has converged after 142 iterations. Now we can calculate the temperatures in report definition. From the report definitions, we find the temperatures for outlet and the PV top average 310.77 and 311.25. Now the solution is all done. Now we have to go back to CFD post processing. After we're done with the solution, now we can go to results, opening results. Now here we are in the results tab. We need to first of all create a line on which we can show the temperature and the coordinates for this line in all domains 2-point system. 0, this is the x, this is the y, this is the z. So it starts from x0, which means over here. This would be x0, y 0.003. It should be the depth, and 0.27 is the distance from here to here. Because the total distance is 0.54, half of it is 0.27. So this line is at the middle of the PV. With the line has 0.63 millimeter length, 0 to 0.63. So sample would be 63. So for each 0.1 there is one sample. Then to visualize our result, we need to draw contours. This is a tube water interface for temperature, and it will show the temperature of water. And this is the contour for the PV top. This will show the temperature on the top surface of the PV. After all this, we can add a chart. XY line chart. Title doesn't matter. Data series, in the data series we need to show the location as line 1. X series is the bottom series. We're going to put that as X, and Y series we're going to put as temperature. Line display settings, chart display, all the same. We're going to apply. and this is the temperature at the line at the middle of the PV. From here we can export this data. It will be in the form of Excel table. Then we can form a chart like this in Excel, in Word, in everywhere. With that, the tutorial is over. Thank you. Have a good day.